All righty. In this one, what I want to look at, excuse me, what we're getting into on this one is something called bond enthalpy. We've kind of talked about this before, okay? But this is another thing we can use. Ultimately, we can use this as a route into delta H naught of reaction, okay? All right, so bond enthalpy, we've referred to this before as bond dissociation energy, or the BDE, because we talked about this before we had enthalpy, right? This is the energy that's required to break a bond, okay? Not too shabby, okay? Hold on a second. Okay, energy required to break a bond. So we can use this as a way to estimate delta H. And I say estimate delta H because there's a lot of different bonds out there, and the bond energy themselves, the bond enthalpy itself, is going to vary a little bit from the type of molecule the bond is in. So really bond enthalpy or bond dissociation energy that's presented in tables of data are the average of all different kinds of bonds that are the same atom stuck together. Okay, so we call this more of an estimate of delta H as we do that. Okay, for this one, we're going to look at an example, and we're going to look at taking methane and reacting it with chlorine gas to make methyl chloride, CH3Cl gas, and HCl gas. Okay, this is an organic reaction. It runs by radicals. It's catalyzed by UV light, all this fun stuff we'll talk about when we get to organic chemistry. We're going to use this as a way to focus on bond enthalpy and how to do this. Okay, this is going to require us to figure out what bonds are broken and what bonds are formed in a reaction. Okay, so it's best we dive in and draw Lewis structures to these things. Methane looks like this. Okay, Cl2, that's easy enough. Okay, this is going to give us methyl chloride, like so, and an HCl. Okay, now we just have to decide what's broken and what's formed. Okay, bonds that are broken end up on the reactant side, so we'll call this side broken. Okay, in order for this to work, we have to break the Cl-Cl bond, and we have to break one of these CH bonds. Okay, it can be any one you want. We're going to break that one. The bonds that are formed show up on the product side. Okay, so the bonds that are formed show up on the product side. We know we have to form HCl, and we're also going to form a CCl as we do this. Okay. Ultimately, our bond dissociation energy will let us figure out delta H naught of reaction. This is going to be equal to the sum of the bond dissociation energy broken minus the sum of the bond dissociation energy formed. Okay, so we're going to do broken minus formed as we do this. All right, let's look at this. All right, so this is a table of bond enthalpy. This is the same idea of bond dissociation energy. And this is just a picture of literally what I just talked about. Okay, on this side, we're going to put energy in to break these bonds. We're going to break one CH bond and a Cl-Cl bond. Okay, that's going to make H atoms, Cl atoms, this methyl thing. Okay, and then we're going to get energy back out by forming a bond here and forming a bond there to make methyl chloride and HCl. Again, this is another application of Hess's law, right? And the delta H of reaction is going to be the sum of these things that happened. Okay. All right. So let's take a stab at this. We said our broken ones were CH and ClCl. So let's find CH and ClCl. Here's our big old table. Okay, here's CH broken. Okay, so broken. We have 413, and we're going to add to that ClCl, which is over here, 243. Okay, that's our brokens. Our formed, all right, broken minus formed, so we're going to subtract the formed, come back, the formed. I wanted blue. There it is. Okay. Formed. Okay. The bonds we formed were a CCl. So find a C. Here's CCl right down here. 350. And we're going to add to that the HCl. We find HCl. There's HCl. 431. Okay. Again, it looks like I'm doing this without units, but we can be sneaky and say this whole thing is going to have kilojoules per mole. Okay. This will give us delta H naught reaction. Okay. All right. So calculator time. 413 plus 243 is 656. So 656. And I'm just going to go ahead and write it because it's easier to do that at this point. Kilojoules per mole. And we're going to subtract from that the formed stuff, 350 plus 431, which is 781 kilojoules per mole. Okay. And then we're going to actually take the difference of those two things now and say 656 minus 781 is negative 125 kilojoules per mole. Okay. Not too bad. Okay. There we go. Just to remind ourselves, this is an estimate. If we do the experimental, the delta H for this is negative 101 kilojoules per mole. That's okay. We're close. We're in the ballpark. Okay. Does that make sense? If you have questions or you need me for anything, let me know. We got to find bonds broken, bonds formed, and count them up. Sometimes there's multiple bonds formed and broken. So we just got to pay attention to what's going on and spot the broken and formed and add them up. Broken minus formed. All right. I'll catch you later. Have a good night.